In this video, we're going to talk about electric power and energy, and especially what formulas to use and how to do calculations related to electric power and energy. Now, the whole reason that we're interested in electricity is because electric energy can be transformed into other forms of energy. All appliances that are electric can be transformed into energy that's used in cell phones, light, home theater systems, television, sound. In fact, frequently we use a lot of electric energy. So that's the whole reason we're interested in electricity. So we want to know how to do calculations for electricity. Well, let's ask how electric power and energy are related to the simple circuits we've been using, where we had a battery and a light bulb, even simpler than what we were doing in class. Well, we can say that batteries are pumps, and the battery pumps charges from the negative terminal up to the positive terminal. So we have a deficiency of charge here and an excess of charge here, and the work done by the battery to pump charges up to the positive gives them potential energy here. So as the charges go through the wire, they are at high energy, and then when they go through the light bulb, they lose their energy. So the energy supplied to the charges in the battery is equal to the energy that the charges lose in the light bulb. So electric energy is converted into light and heat energy. Definition, and this should be familiar to us from January. Power is the rate at which energy is used, or the rate at which work is done. In the case of electricity, we would say power is the rate at which electrical energy is supplied to a circuit. So in terms of a formula, we could say that power is either the work done by the battery on charges per time, or it's the rate that the battery is delivering energy to the circuit. But in either case, it is an amount of energy per time. So on the reference tables, what we saw was power equals either work or energy divided by time. The units for energy were joules, so if the battery is supplying 1 joule of energy per second to the circuit, then we would say that the battery is delivering energy at a rate of 1 watt. So a 60-watt light bulb that you have at home means your light bulb is delivering 60 joules of energy in the form of heat and light every second into your living room. So how can I calculate power or wattage for electrical devices? What formula would I use? Well, let's build a formula. First of all, we know that power is work or energy divided by time. We also know that electric potential, that's an electrical thing, is energy per charge. And we've also learned that when charges move, there is a flow rate that we call current. So first of all, what we're going to do is we want to use power is energy per time, and we're going to make a substitution into here. We're going to solve this formula for W. So I'm going to use V equals W over Q, and that's going to give me W equals V times Q. So energy equals pressure times charge, and then I'm going to substitute that in to power equals work divided by time. So power is work divided by time, and we're going to substitute in that energy is also equal to electric potential times charge, and still divide that by time. But then we notice something interesting. I have charge divided by time, and I remember that that's current or flow rate. So instead of power equals energy over time, it's the same thing as power equals electric potential difference times current, or pressure times flow rate is power. And let's just see how that works with units. Power equals electric potential or pressure times flow rate. Let's see how the units go. Units of electric potential are volts. Units of current or flow rate are amps. A volt is a joule per coulomb, energy per charge, and an amp is a coulomb per second. It's the rate that charges are flowing. And I notice what happens is the coulombs cancel out, and I get joules over seconds, which we just said that's watts. So apparently, when I multiply volts times amps, I truly do get watts. So power is electric pressure times flow rate. So let's try a couple of Regents questions related to this. First of all, what is the power of a heater that draws 12 amps of current when it is plugged into a 120 volt outlet? So I'm looking for power, current, and pressure or voltage. So the formula that I would use is power equals electric potential times current. So the power is simply going to be the product of 120 volts times 12 amps, which is going to give me 1,440 watts. Or we could try this one. Find the current in a 60-watt light bulb that is plugged into a 120 volt outlet. So once again, I need something that has current and voltage, and I can see I have wattage or power. So again, the formula is going to be power equals potential difference times current. And in this case, I want to know the current, so I'm going to divide both sides by potential to get the current by itself. So I want current equals power divided by voltage, and the power is 60 watts, and the voltage is 120 volts. So I have 0.5 amps of current in this light bulb. Now before we move on, let's ask another question here. If I have a high voltage or pressure difference, do I always get a high current or flow rate? If you remember when we talked about this before, the answer is no. How much flow rate I get also depends on the resistance that the pressure difference is across, or the resistance that the charges are going through. So if I would like to use power equals electric potential times current, I need to have some way to get resistance in there too. So how do I get resistance into something with electric potential and current? And the answer is I do it through Ohm's law. Resistance is the ratio of electric potential to current. Now, it turns out that we would like to be able to get R in here or R in here. So what we're going to do is solve this formula for V, and then we could put it in here. That's one way to do it. Or we could solve this formula for I and put it in there. And here's what that would look like. So first of all, let's say I want to solve Ohm's law for V and substitute it in here. So to solve Ohm's law for V, I would multiply both sides here by I, and that would leave me with V equals I times R. So this is another way to write Ohm's law. If I want to solve Ohm's law for I, then I would start with this, multiply both sides by I again, and then divide both sides by R, and I would be left with I equals V over R. So the point of this is that Ohm's law can be written in three different ways that I can use to substitute in here to get different versions of this formula that have resistance in it. Let's see how. So I could write power equals potential difference times current, but substitute in from Ohm's law, instead of V, like we just did, write I times R instead of the V from Ohm's law. Then I'd have I times R times I, which is I squared times R. Or what I could do is start with pressure or power equals electric potential times current. And now, instead of using the I here, I'm going to substitute I from Ohm's law. And what I will get is that I will have voltage. Now, if I write current from Ohm's law, it's V over R. So then I'm going to have V squared over R. So now what that means is I have multiple ways to solve for power in a circuit. I could use voltage times current. I could use current squared times resistance, and I could use voltage squared divided by resistance. And all three forms of this formula will help me find power. And notice on your reference tables, that's exactly how the power formulas are representative. So P is voltage times current, or it's current squared times resistance, or it's voltage squared divided by resistance.